Hello again. Now this describes how we can size water supply reservoirs in an Excel sheet. So if this is your given map, which gives the percentage of average day and the time of the day. So usually this explains the maximum demands over a day, which means the hourly demands. And the lower curve indicates the typical winter day demands, where you have much rainfalls and the consumption for the water supply from the normal lines will be decreased, because there will be small buzzing, there will be the decrease in temperature, so the water requirements for other purposes like washing will also decrease. As a result, there will be smaller demands. And in the time of the hot times, or in the dry seasons, the only water supply source will be the normal water supply pipe system. So in that case, we use the water for washing, for cleaning, and for drinking purpose also. It will be higher. So this indicates the percentage of demand in an average day, and so this is in a form of percent, which means it is as a percent of the average demand. So if you can collect data from this curve, from the maximum one, because we are designing a reservoir, and the reservoir should be capable to store the water during the maximum time. So we can collect points at different times from here. So if you see, for example, at time 12 a.m., we have like 100% of average day. So we can write that here as 100 at 12 a.m. And then if you check at another time here, you have 4 a.m. for example. 4 a.m. it is like this is 100, and it is like 120 or something like that. So you can come here, and at 4 you can see it is 110, nearly the same. So you read the data in the same way over these curves. Okay. Now we have a time interval data. This is in a form of percent. So this is a high scale in a form of percent. In a form of what percent? It is in a form of the average day demands. So let's consider the average day demand as the maximum demands, or the maximum percentage here. So you can see this is the maximum percentage, which reaches to like 275. So let's see our data as a ratio of the maximum demands. So sorry, in a form of percentage to maximum demand. Okay, percentage to maximum demand. This will explain that if you have a maximum demand, you can assume any maximum demand, but usually you have to determine it from the population's need. So let's say our maximum demand being 600 meter cube, or 600 liter per second. Okay. So the percentage to the maximum demand, which means in a form of percentage, this is going to be the maximum percentage. So let's express the other in a form of this one. Okay, which means we can say this is equal to this over 274, because the highest percent, or the highest percentage, or the highest demand in our case is 274. And for that value, you can calculate your data in a form of percentage, and here is what you get. So you can fix this column data. If I say format sales and numbers, I fix it to 3 digits. That's good enough. So this is a percentage demand. So this is the maximum demand. We write the data as a percentage of maximum demand. So the flow out in a given the flow out in a given time should be the same as the demands. At the same time, the flow in should be calculated from the required demands. So the demand, which is the flow out, okay, flow out is equal to the percentage times the maximum demand. Okay, so you can fix this with a dollar sign because it is a constant value. Then this is your flow outs, and usually this is in a liter per second. Okay, and usually the flow in okay, the flow in should be equal to the average day demands. So if you take this one as an average, okay, the average will be 380, as you can see it, and now we can write 380.56 here. So average demand 380.5656. So this is average demand. So flow in should be equal to the average demand. So we have this value, and fix it with a dollar sign. Okay. F4, and here is your value. So this is also in a liter per second. In a liter per second. And now if you want to get the flow in and the flow out in terms of volume, we have to express it in a form of this time span, and then in a form of the meter cube. So if you want to convert this to meter cube, so this is in a volume in or volume out. Volume in, for example, is in meter cube. How can we express this? So this is our volume in, for example. So if you multiply this by the time, so the time interval is here. You can see here the time interval is 1 hour. So 1 hour times 60 minutes times 60 seconds, which means you have converted this into a liter completely. So if we divide this value for 1000, then to be in a meter cube. So this is your volume in a meter cube, volume in, and volume out, and it will be in a meter cube again. So do the same thing for this one, which is equal to volume out times 1 hour times 60 minutes and times 60 seconds, and over 1000, it will give you the volume out in a meter cube. So this is your volume out, and then now we can check the change in volume, d in volume in meter cube. Okay, the change in volume. So that is equal to volume in minus volume out. Okay, so you can find that. You can see at some places you have a negative value, at some places you have positive value. You have a positive value means the volume in is greater than volume out, so there is a sufficient water. And it is negative means volume in is less than volume out, so there must be an additional water that should be stored in a reservoir. So this is what we get. So the minus sign, you see, it is being decreasing to minus 742. So in order to allow in order to find 0 points, or where the reservoir becomes completely empty, we would like to move this time to the top, because it is positive, which means in between these points somewhere there is a reservoir 0 point, because this is negative and this is positive. So take this time, because it is a continuation of the 12 a.m. is a continuation from the 11 p.m. Then we can move this row okay, to the top. So you can move this row to the top, and this is your change in volume, and then you can find the total storage. So accumulated storage, which is in meter cube. Okay, the accumulated storage will be equal to the storage at time t plus the current storage plus the previously existing one. So at this point we can consider it it is the same at this value. Okay, if the previous storage is 0. Okay, so this will help us to assume that the previous storage is equal to 0, because we have seen that the negative changing to positive, and in between that point we know that is a positive, there is a 0 point. So this is, if 0 is the previous storage, so the previous storage plus the currently created change in storage will be the total storage available. Then when you come to this time 12, so this current storage in your reservoir will be the previously existing storage plus the additional storage that is being created from 11 to 12. So with that perspective, you can calculate for all the data you have. And then if you see here, so we nearly reached very 0 point. So if you fix these data into 2 digits, for example, format cells and to 2 digits, okay. So you have or to 1 digit. This is a huge number, so we can fix this to 1 digits. If you fix it to 1 digit, so you'll see that you will find a 0 point at time t is equal to 10 p.m. So your storage will be the maximum of this one. So you have to find the maximum. So you can say just equal to the maximum, and again select this data and find the maximum of this all. Okay, close your brackets and say equal. So 337.55.03 meter cube is the total storage amount that is maximum in our time span. So which means your reservoir should be capable of carrying at least this volume of water. So this is the calculated volume. V calculated is equal to 3775.03, and V for safety. You might consider like usually you consider like 10% of the total one. If you consider like 10%, which is 100, so this is for safety value. So V which is for design should be equal to this plus this one. Okay, so this is the total volume for which you should be designing your structure. Again, when you design a structure, we can determine the diameter and the height of our structure from this volume. But when you do that, you have to allow an opening space in the reservoir, because you don't fill the water to the top of your reservoir. So this is how we come up with the maximum volume for which we have to design our structure. So if you see in this case, the volume, positive volume or accumulation volume will increase and reaching 3755 at this point, okay, and then start decreasing. So that is the maximum storage that our structure needs to carry. So this is it, and that is how we come up with the maximum storage design.